So today we're going to be looking at the study guide for Chapter 10 for statistics, which is on regression, mainly focused on linear regression, but we also do some nonlinear regression at the end there. So the first thing it asks is what are the three types of deviations we talked about in class. So remember, we basically had, as it says here, three types of deviations that we were looking at. We had total deviation, explained deviation, and unexplained deviation. So total deviation was basically how far away the average was from the actual values, usually of y. So this was the actual value of y minus the average of value of y. So how far away our point that we're looking at, our instance, our 1 unit, how far away that was from the average of what we usually got. The explained deviation is how far away our predicted y value, so how far away our regression line y value was from the average, so minus average. So how far away were we, or how far off from the average was our prediction based on our regression equation? And the unexplained deviation is the other part. So it's the actual value minus the predicted value. So basically it's how far off we were in our guess. So if we predicted y was 10 and the actual value was 25, then our unexplained deviation for that was 15. Basically, this unexplained deviation is how far off were you from the actual value based on your predicted guess. So that's all there is to it. Again, it's just a matter of making sure we know kind of what each one represents. Total deviation is from actual to average. That's just the entire span of things, how far off your actual number was from the actual average, whereas explained and unexplained deal with your predicted y value and looking at how far that way is from the average or the actual, respectively. So number 2 here says the line of best fit is this, where x stands for the score and y stands for the dollars that they earn, and use this to find the predicted score it would take to earn $100. So I would rewrite my equation here. Y equals 6.5 x minus 4. It says find the predicted score to earn $100. So we know we're going to earn $100, and it says here y stands for the number of dollars. So we're going to take 100 and put it in for y. So 100 is equal to 6.5x minus 4. And then you just solve the equation. So add 4, we get 104 is equal to 6.5x. And then we divide by 6.5, divide by 6.5, and we end up getting, do this real quick, 104 divided by 6.5. Whoops, that's 140. Let's try it again. 104 divided by 6.5, and we're getting 16. So based on our equation, we would have to get a 16% to earn $100, which if we check it, if we plug this back in here, 16 times 6.5 minus 4 does indeed give us back to being 100. So a pretty easy way to get $100, I'd say. But that is what this equation tells us we have to do. Next one here is testing dogs. So it says a test is run on 50 dogs, tracking the time it took them to fall asleep after eating a certain food brand. The correlation coefficient is this. What are the critical values if we're using a 0.05 significance, and what's the conclusion? So the critical values is where you get your numbers from A6 when you're testing a correlation. So we're going to go over here to A6. There it is, table A6. On the left-hand side, we have our N, which they said that they were testing it on 50 dogs, if I remember correctly. Right, 50 dogs. So we're going to look for N is 50 right there. And it says we're using a 0.05 significance, so we're using the first column. So my critical value is going to be 0.279. So let's write that down in there. So this is going to be 0.279. And so that's our critical value. That's plus or minus 2 because it is always a two-tail. It says, what's the conclusion? Well, our conclusion is depending on whether r is more or less than the number. So it's the absolute value of r, or just the positive version of r, which is 0.987, is indeed greater than 0.279, plus or minus. So that means that it supports, not says there is, but just supports correlation. Why? Well, because our R value was bigger than our critical value. So R value beats critical value. Whoops, try that again. Beats critical value. So therefore, we say that it supports the fact that there's a correlation. Next one here was where we get the meat of the stuff. So it says, okay, you have a list here. Find the equation, the correlation coefficient, proportion of variation, all that good stuff. So let's type this in here. So let's make sure we enter our numbers into our lists correctly. So we go edit lists, and let's enter this in here. So we'll do the age as X and the heart rate as Y. So 20, 25, 30. Depending on who you are, this can be kind of therapeutic, entering in data. 45, 50, then we go over. 135, 132, 129, 25, 122, 119, and 115. That looks correct. Let's check that one more time here. 35, 25. Right. So it's always good to double check your list before you continue, just so you don't make any silly errors and have to go back and redo everything. So once you got your list entered, if you want the equation, what you do is you go to stat, calc, all the way down to where it says linear regression ax plus b. Excuse me. So number 4, because we want the mx plus b or the ax plus b form. We hit enter. We hit enter again, and it pops this up. Now mine didn't give me my R, so I have to go to my diagnostics. So I'll do second catalog. Go down to the D column, so we'll press this to get down to the D column, and turn their diagnostics on, and then we'll try that again. So there we go. So that looks more like what you see on our screen. So it's negative 0.664, try it here, negative 0.664 x plus 148.54. And that's equal to y. And so it says, what's our correlation coefficient? Excuse me. Our correlation coefficient is just another fancy word of saying R. So our R here, negative 0.999, is our correlation coefficient, negative 0.999. Which means it's a pretty strong negative relation, right? It's pretty close to negative 1, so that'd definitely be a pretty strong negative correlation there. So as your pulse rate, or sorry, as your age goes up, your target heart rate goes down, which again makes sense why that's a strong correlation. What is the portion of variation? This right here, this fancy word, just means R squared. That's it. So R squared is, whoops, my R squared is 0.998. So 0.998. So what this means is about 99% of the reason that a person's target heart rate goes down is because their age goes up. So again, not all the reason, there are other factors as well, but that's kind of what that means there when it asks for proportion of variation, is what percent or how much of y is changed because of x. But as long as you know it's r squared, you can get the value no problem. Test the data to see if it's strong enough for a correlation using a 0.01 significance. So when it says test, we want to put our r, which is negative 0.99, up against a critical value and see who wins. So I already saying that the correlation coefficient winning, but we should always check it. So we're going to go to table A6 and use 0.01 as our significance. So table A6, 0.01 as our significance. It doesn't say how many we surveyed, so let's go back and look. So we have 1, 2, 3, 4, 5, 6, 7. So we have 7 people that we need to survey. And so that means we're going to have 0.01, 7 is our n. To find out where they cross, we get 0.875. So my critical value is 0.875 from table A6 again, and my R value is over here. Now, when you're comparing this, you should always compare the absolute value of R, just so you don't mix positive and negatives together. So it's really like 0.99 positive is greater than, oops, let me try that again. 0.999 positive is greater than 0.875. So this would be supports correlation here. So supports, doesn't say there is, but just supports correlation. So when you're comparing R to the critical value, don't forget to make the R positive just because it makes comparing go a little bit easier, and it's a perfectly fine way of doing that. So we have another set of data here. We have a regression equation after 20 rare animals. It says that the R is 0.775, which is not that high, and that the average amount of money that they earn is $470. Excuse me. What's the best predicted value for the amount of money we'll earn if they kill if they kill 6 unicorns? So when it says what's the best predicted value, that means they're looking for either alpha or, whoops, sorry, let me try to erase that there. Not alpha. They're looking for either the average, so average, or equation. I'll put EQ for equation. So when you're doing the best predicted value, you're looking for either the average or the equation. How do you know which is which? Well, or sorry, how do you know which one you use? Well, it depends on whether your equation passed the test. So in our case, our R is 0.775. We want to compare that to our critical value and see if it wins. If R wins, then we're going to go ahead and use the equation. If R loses, then we're not. So in this case, we have 20 rare animals, that's N, and we have a 0.01 significance level. So we go back to table A6. 20 is my N, 0.01 is my significance, so it's 0.561. So 0.561. Well, R definitely beats that. Excuse me, yawning a lot. R definitely beats that. So that means that since R wins, we're going to use our equation as our best predictor there. So we're going to take our equation and plug it in. So we're going to have 25 times 6 plus 10. So all I'm doing is taking this equation and replacing x with 6, because x represents how many unicorns they killed. So in this case here, we do some arithmetic and we get that equals out to be $160, or $160. So when you have an asking question about what's the best predictive value, that means you should always check to see if the average is the one you're going to go with, or if it's strong enough that the critical value is less than R, so you can just use the average as your guess. Like for example, let's say R was 0.257 instead. Well, in that case, 0.257, let me try to write that correctly here. Having trouble keeping my pens on track. So 0.257 is definitely less than 0.561. So in this case, we wouldn't use my equation as my predictor value because it's not as accurate. It's not accurate enough, at least. So if your R value loses to your critical value, then you simply use the average as your estimate. So my average guess would be $470. Why? Well, because my equation isn't good enough to use as a predictor value, so the next best thing is to use the average as the best predictor, because average is usually a number or value within the middle of the data, so it should be an okay way of predicting stuff. But that's only if your R loses. In this case, these are just quick questions here. If R is close to 1, it's considered to be a positive correlation. If R is close to -1, it's considered to be a negative correlation. It's just as simple as that. The closer it is to 1, the stronger positive it is. The closer it is to -1, the stronger negative it is. So you can add strong and weak there as well if you want. The last one here asks us to figure out what model best works. So right now we have 3 models. We have linear, we have exponential, and we have logarithmic. And we want to figure out which one of these best fits this data. So what you want to do is first enter in your list and just to test to see which one has the best R. So my numbers here are 1 through 5. So 1, 2, 3, 4, 5. Whoops, 3, 4, 5, 4, 5. And then we delete, delete, delete. Okay, and then we go back up and we say, okay, this is the years that they were in business, and the Y is the profit that they make. So that's going to be 35, and this is in thousands of dollars. So 35,000, 54,000, 89,000, 127,000, and 195,000. So those are all the values that we have. Again, the Y column here is how much money they earn, and the X column is what year they earn it on. So first year, second year, third year, fourth year, fifth year, and so on. So which one of these works best? Well, we're just going to go through, stat, calculate, and figure out what our R's are. So if we try linear regression, we get an R of 0.975, which is not bad. So 0.975, that's our R value. If we go to exponential instead, so stat, calculate, exponential. Let's see where they hid that. There we go. EXP-reg is what it is. Hit that. In this case, our R ends up being 0.998, which is pretty darn close. 998. Let's see if your logarithmic calculator does anything different. So stat, calculate, and in this case, we're going to go down to where it says, whoops, too far. We're going to go over to where it says LNREG, which stands for natural log regression. We hit that, and we get an R of 0.904. So of all these data sets, they all work pretty well because they're all in the 90 range, but exponential is the one that works the best. So we're going to go with that as my predictor. So it says predict how much they'll earn in 8 years. So let's go ahead and go back to my exponential equation. So stat, calculate, exponential, which is all the way down here. Enter, enter, and let's get our equation down. So it's already in that form for us. So A is 23.17, and A is right there. So 23.17 times, whoops, let me try again. In this case here, my B value is 1.54 essentially. So 1.54 to the X. So that is your typical exponential equation for this data set here. We have our A value here, we have our B value here, and then our X value would go on the top depending on what we decide to check. So it says here, predict how much profit the company will earn in 8 years. Well, X is my years, so this will be years. This is dollars, probably should leave it first. So X is my years, so that means I'm going to do 23.17 times 1.54 to the 8. Just replace X with the number of years. And in this case, we end up getting about $717.139,000. So it's pretty impressive. Exponentials do tend to go pretty quickly, so that's why you can kind of tell automatically that, hey, this is going pretty quickly, so it's probably going to be an exponential. Just an FYI there. But when you have that question, make sure you check all 3 types of regression. We also had a quadratic regression, so quad. If you don't remember how to do that, we go to same deal here. We go to stat, calculate, and we just go down to quad regression. Hit enter, and we get an R squared of 0.997. They don't give us an R for some reason, so 0.997. You can square root that to see if it's better than exponential, but given that's already so close, it's probably not going to be that big of a deal. So exponential would be the best way of going back here because it has the highest R, and vice versa. It also has the highest R squared, if we could see it, from one back. But as long as it has the highest R value, that's the one you're going to use to your model, and then you just follow the same steps in your calculator to graph it as a linear equation. So that's all the questions that you might have on your quiz. Again, look through them, video, ask me if you have questions, but hopefully that goes well. If you have any questions, let me know. Otherwise, hope you enjoy the video. Have a good day.